Hello and welcome to class number 34 of Physics 218. So last time we began our discussion of scattering from a potential energy step, something that looks like this. Today we will look a little bit more at how to analyze that mathematically. Some of the details I will postpone to a bonus video, but we'll talk a little bit about the analysis and we'll further explore some of the conceptual issues that arise when thinking about scattering states. So to warm us up and to recollect what we were thinking about last time, I'd like us to begin with a clicker question. Hopefully you've had the chance to think about this. So as you remember from looking at the PhET in the last class, right, when we have a plane wave incident on our potential energy step, there is some probability for that plane wave to be transmitted and some probability for it to be reflected. I would argue that the best answer here is really because this is a general phenomenon with waves, as we talked about last time with examples like a spring with a mass density discontinuity, or looking out a window. What I can also say is that we should be clear that the particles do not have a range of energies. Namely, we're looking at scattering state solutions to the time-independent Schrödinger equation. I think I need to get a new marker, but we're looking at solutions to the time-independent Schrödinger equation that have definite energies, or in other words, they're energy eigenfunctions. Right. There's a the energy eigenvalues are continuous in the sense that they can take on a continuous range of values, but for these solutions, they're states of definite energy. So I now want to outline how one can analyze this mathematically, and let's start with the case where the total energy of the system E is larger than V naught. This is the case where we started off looking at in the PhET, where we have propagating, transmitted, and reflected waves. And we assume also that that we have a beam of particles, so a plane wave incident from the left. Assume plane from x less than 0. So previously, right, we talked about sort of a general procedure for solving the time-independent Schrödinger equation. That's what we're going to do here, and these are not bound states, but the overall procedure is still pretty similar. So to outline what we're going to do, so we have sort of a piecewise potential energy here, right? So here the potential energy is 0, but for x greater than 0, V is equal to V naught. So we write down general solutions to the time-independent Schrödinger equation for our two regions, and x greater than 0. And the second important thing we're going to do, like we did before, is to apply boundary conditions. So that's as far as I'll go in the sort of general, in the main video. The going further involves a little bit of subtlety in terms of thinking about a probability current that I'll save for a bonus video, but I want to do enough of this to give you a flavor of how this goes, even though after this we'll sort of jump ahead to the result. So like I said, the first step is to try to write down general solutions to the time-independent Schrödinger equation. Let's start by doing this for x less than 0. I think you might already know what the answer is going to be, since we've dealt with potential energy being 0 several times already. Right, my TISE is going to take the following form, where v is 0. I am going to get d squared psi of x dx squared equals 2 minus 2 m e over h bar squared times psi of x, right? So this is probably not too much of a leap to say that this is, we can define this as minus k squared psi of x, right, with k as usual. And we'll interpret this as a wave number, and k, right, will just be the square root of all of this, so equaling root 2 me over h bar as usual. So I think you can sort of see from the form here, right, that we've seen this kind of thing a couple of times, and so it's going to be oscillatory, right? So it could either be sines or cosines, but it turns out it's easier to work with complex exponentials here. So we write down our general form of solution as psi of x equals some constant times e to the ikx. But remember that e to the minus ikx also satisfies this, so I need to include that as well to get the most general possible solution, e to the minus ikx. Now, sort of physically, let's think a little bit about what these two terms mean, right? So we've talked about e to the ikx, and if we remember that these are states of definite energy, so if I were to tack on the time dependence to get the full wave function, right, it would get a factor of e to the minus iet over h bar. Or so something that goes like e to the ikx minus I omega t, is a plane wave that's propagating to the right. So we identify this term because it's going to the right, and we're assuming that we have an incident plane wave that's going that way. We associate this with the incident beam. Similarly, this second term here, it goes like e to the minus ikx. This is going to represent a plane wave that's going to the left in the minus x direction. Perhaps the easiest way to think about that, again, if you tack on the time dependence, you're going to have something that goes like e to the minus ikx minus I omega t, and that will be a waveform that's going to the left. So physically, if this is going to the left, we can identify that with the reflected portion of the wave. Now, for x greater than 0, the time-independent Schrödinger equation is going to take a slightly different form because my potential energy is non-zero for positive x. And my TISC is going to become, I still, if I isolate my derivative here, my second derivative here, I'm going to get a minus 2m, right? This time E, right, minus V naught over h bar squared times psi of x. Right? So this still has a pretty similar looking form, and the reason it does, right, is we're assuming that E is larger than V naught, so that this, so E minus V naught is positive, and we have minus like a positive definite thing times psi. So following Townsend's notation, I'll define this as another k, namely I'll call this minus k naught squared psi of x, and this time the k naught will incorporate my v naught with k naught defined as root 2m e minus v naught, oops, over h bar, right? Notice that here, right, my k naught is smaller than my k before, right? Smaller a smaller k naught here means that the wave function on the right has a longer wavelength, which jives with what we saw in the PhET simulation. So what are the solutions? They're going to look quite similar, right? So I can write down sort of pretty much the same thing, just with k naught instead of k. So we'll still have this term c e to the I k naught x. But then, let's think about what else, right? Do we want to include a term that goes like d e to the minus I k naught x? So here is where we have to apply a little bit of physics, right? Because we know that, right, we're sending in an incident plane wave from the left, some of it's getting reflected, some of it's getting transmitted, but there should be, that's nothing that's coming, from right, going left in this region, right? All our particles are incident in this way, right? And if whatever is transmitted is going to have to be going to the right. So on physical grounds, right, because this represents something going to the left, we will cancel that out, right, because it doesn't jive with the physical situation of doing an experiment where we're scattering particles from the left. So let's just write down y, and physical transmitted wave moving to the right. Okay, so at this point we've written down the general form of the solutions to the time-independent Schrodinger equation here for negative x, and now for positive x. We have to stitch them together by applying boundary conditions. So our next step will be to apply boundary conditions at where we need to stitch the wave function together at x equals 0. So if you remember from our analysis of the finite square well, what were the boundary conditions we had to apply then? Remember how we talked about we have to require two things, right? Psi, the wave function, has to be continuous. Number two, the first derivative of my wave function also has to be continuous. So psi of x, continuous. and then d psi dx is also continuous. So at this point, it basically turns into an algebra exercise, which again, I'll go through some of this in the bonus video, but I think you can sort of see how the game ends up getting played. Now, you might have a concern, which is we have three undetermined coefficients, A, B, and C, but only two boundary conditions to apply. Previously, that wasn't a problem because there was always a constant, an overall multiplicative constant we could determine by normalization. However, remember that these plane wave functions aren't normalizable. So that turns out to be a little bit tricky to deal with, and I'll talk about that in the bonus video. The solution ends up being to define a reflection coefficient and a transmission coefficient that has to do, right, so for transmission, it ends up having to do with the ratio of C modulus squared to A modulus squared, and similarly for reflection, it's looking at the ratio of these two coefficients, B and A. But it is solvable how to think about this, even at least thinking about the probability of transmission or reflection, even if we can't have an ultimately a normalizable. These solutions aren't normalizable. If you need to represent like a truly localized particle, remember that you can always build up a wave packet by superposing a bunch of plane waves. The scattering of a wave packet is a really interesting problem. It's sort of, and you saw it in the FET, right? But the mathematical analysis of that is sort of too messy for us to deal with. Let me wrap up this section by saying a few words about how to do the analysis when E is less than V0. And again, as you saw in the FET, right, in this case, what we end up with is a wave function that looks like it decays into the classically forbidden region, x greater than 0. Well, that turns out to be exactly what comes out when we do the mathematical analysis. Stepping back to writing down the general form of the solution to the time-independent Schrodinger equation, nothing changes here. The only difference is there. For x greater than 0, my TISE gives me so a d squared psi dx squared. And this time, because E is less than V0, I'll sort of flip the sign in, and this will give me a 2m V0 minus E over h bar squared psi of x, right? Or this time, now this whole thing is positive. This we will write as kappa squared psi of x, right? With kappa defined as root 2m V0 minus E over h bar. Hopefully this looks pretty familiar from what we did to analyze the finite square well. It's basically the same thing. I could now then go with that work and write down the general solutions, right? So we have C this time e to the, I'll do C e to the kappa x, right, plus D e to the minus kappa x. So we do in fact see that we've got something that's exponential-like now, but now we have to put on our physics hat again and think about whether both of these terms make sense. This time, it's going to be this term, proportional to e to the kappa x, that is unphysical. And the reason this is unphysical is because it blows up as x approaches infinity. Approaches infinity. Right? And I'm not going to try to sort of prove it in a rigorous way, but you might imagine that sort of explicit blowing up is in some sense mathematically sort of even worse behaved than just oscillating the way like a plane wave does. So like it's sort of even more unnormalizable. And just because it just doesn't make physical sense to have something where like the further away you are, the more and more likely you are to find your particle. We reject this solution. And what we end up with is, in fact, something that's exponentially decaying in the classically forbidden region here. And as you saw, right, from in the FET, and should be familiar with the finite square well, right, if my E is just a little bit less than V naught, right, then my kappa ends up being small, right, and then e to the minus kappa x with a small kappa means that I sort of slowly decay and like penetrate a significant distance into the forbidden region, whereas if E is much less than V naught, my kappa gets big and the wave function dies off quite quickly. So I want to wrap up today's class with two clicker questions. So let's take a look at the first one now. So as you saw in the FET, right, when we the wavelength is longer for x greater than 0. Right? And as we've seen with just regular plane waves, a longer wavelength, right, is associated with a smaller wave number k, or in other words, a lower kinetic energy. This also jives with what we expect from looking at an energy graph like this, right, where you know that the kinetic energy is the difference between the total energy of the system and the potential energy. So our kinetic energy here, right, that's smaller for x greater than 0. The last question we'll look at is thinking about what might happen if we have particles incident from the right. So take a minute to think about that, and then I'll cut to the FET simulation to look at the result. So you see now that I've set up the step potential again, but this time I've got the incoming wave coming from the left. Coming from the right and going to the left. I seem to have right and left mixed up. If we now watch time go on now, we can sort of watch what happens here. And again, if I separate this into incident and reflected, right, notice that there's both that some of the wave is indeed transmitted through, but some of it is also reflected back. So this is, again, no different really than sort of you get this exactly the same behavior going, if you have a wave initially on a thicker string going to a lighter string. Again, because there's a discontinuity in the potential energy, because we're talking about waves, we get both transmission and reflection. So today we've continued our discussion of scattering by a potential step. When we come back on Monday, we will look at tunneling through a barrier, so using similar mathematical tools. But tunneling is one of the cool and unusual features of quantum mechanics with some interesting real-world applications. So looking forward to that. See you all on Monday.